So the first question, what are ultrafine particles and why should we be concerned about them?
Yeah, maybe I can show you the first slide of my presentation here with respect to what are ultrafine particles here. So I tried to come up with a definition of those particles. Ultrafine particles, first of all, it's a class of particles below the physical size of 0.1 micrometer or 100 nanometers. So pretty small, and occur in the ambient atmosphere indoors as well as outdoors. There are many sources in both places, indoor sources, but most of all outdoor sources. And chemically and physically, these particles, these ultrafine particles, are very diverse, depending on where they're coming from, how they were generated, and so on. And so the mechanism of formation is very important, and also how they are dealt with in the atmosphere. They can transform there, and all of a sudden we can become a completely different material again here. And they can be consisting both of solid materials, for example elemental carbon, but also soluble materials, certain trace elements or sulfates and nitrates, and as well volatile constituents, so that at high temperatures some of those may come off here. And importantly, they are generated unintentionally. We don't want them to be created, but that's just a byproduct of many combustion processes. For example, power plants emit those ultrafine particles, and many other sources here. And that is one major difference to engineered nanoparticles, which are intentionally generated for a specific purpose and having a specific function, and makes them also very desirable for these processes, whether it's optical, electrical, or mechanical processes, as opposed to ultrafine particles, which are there, and we have to, and there are measures in place how to avoid them, avoid exposures, or to clean up the atmosphere.
Well, I think you pretty much answered the rest of my questions.
Oh,
we
that's
talked
good.
about physical size, shape, and chemical composition. Although,
yeah.
is there a comparison that we can use for the size of a nanoparticle or an ultrafine particle as opposed to what we consider PM 2.5 or PM10?
Yeah, I can. Okay. Let's go to slide here. Here. This shows a typical, or I should say an ideal distribution of different particle sizes in the ambient atmosphere. And you see here typical, I don't know if I can point it out here, probably it cannot be seen. Oh, can you see the cursor? Oh, I can see it here. Huh. There's no cursor here. Yeah. And so there are four modes, and on the x-axis at the bottom, yeah, he doesn't see that.
Oh.
on the x-axis, the size from 100 micrometers, so very big on the right-hand side, down to 1 nanometer on the left-hand side. And you see that these modes are distributed over this whole size range. And the ultrafine particles, or nanoparticles, are below that 0.1 micrometer value here, or 100 nanometer value, and consisting of two modes actually, the so-called nucleation mode, which is generated by nucleation processes in the atmosphere from vapors, certain vapors in the atmosphere. They just condense and form ultrafine particles. And then the Aitken mode particles, also a nucleation process, and depending on the generation, for example, in internal combustion engines, we will see those particles then. A major feature is that both of these modes, the nucleation mode and the Aitken mode, coagulate onto the next bigger mode. And so the nucleation mode coagulates onto the Aitken mode, and the Aitken mode onto the accumulation mode. Mm-hmm. And so that means that this accumulation mode basically acts as a sink to take up the ultrafine particles. And so if you have a lot of these accumulation mode particles, then the ultrafine particles will be coagulating onto them, and then they are gone from the ultrafine particle mode. Now, because there's continuous generation of those, you will always have that mode there. But I can tell you about one incident in Germany after the reunification, where the eastern part of Germany was cleaned up efficiently, and the easiest to do that is get rid of the bigger particles here, the accumulation mode. And as soon as that happened, and the sink was gone for the ultrafine particles, it was noticed that the ultrafine particles all of a sudden increased, despite cleaning up, in quote, the air. And this coagulation phenomenon is one factor that most likely contributed to that.
So they're challenging to measure.
Oh, with respect to measurement, we have instrumentation that will measure the ultrafine particles in the air, and these are start with a cascade impactor, a nano cascade impactor, which goes down to the nano range, but also so-called scanning mobility particle sizes, SMPS, which identify the particles by the amount of electric charge that can be put onto those, that can be measured in that instrument, that we get some idea about the number concentration of the ultrafine particles.
So would they be measured in terms of how many particles are in a volume, or by weight?
Yeah, that is then measured to the output then from SMPS would be the number of particles per cubic centimeter of air, for example. Yeah, and knowing, and an assumption is that we assume a specific density of 1.5 gram per centimeter cube, knowing that we can then also, this instrument also gives you an output about the surface area and the mass concentration of the materials. Surface area is assumed that depending on the loading, electric charge loading, that is more or less a spherical surface. So these are all assumptions. The best is read the number concentration, that is probably the most accurate one. With respect to mass, of course, another method would be to take filter samples. But here you have to make sure that you get rid of the coarse, the bigger particles first, because they contribute most of the mass to the whole thing, and that becomes then a bit more difficult to really capture only the ultrafine on a filter.
So if they differ from other particulate matter in size, in composition, in transport, and exposure to humans, how are they affecting human health?
Well, one thing is to consider the differences in deposition. I can show you another slide here. If we go down, and here, this shows you the deposition of different sized particles in the human respiratory tract. And on the left-hand side of this figure here, it shows the human respiratory tract with respect to the three areas, the three compartments that we like to look at. That's the upper respiratory tract with the blue circle, then the so-called conducting airways from the larynx down to the so-called terminal bronchioles, the green area, and then the alveolar region, the deep lung region, where all the alveoli are where the gas exchange takes place, has the highest surface area. And on the right-hand side of this figure, you see for these different sizes of particles, again from about 1 nanometer up to above 10 micrometer, how particles, if they are in that size, in the airborne state, are deposited. So left of that dashed line here are the ultrafine particles, 0.1 micrometer and less. And as you can see here, the blue line shows you that for the very smallest of those ultrafine particles, approaching less than 5 nanometers, the highest deposition efficiency is actually in the upper respiratory tract. And this is contrary to what most people think, that they think the smaller the particles, the deeper they penetrate into the respiratory tract. Not true, because of a mechanism which we call diffusion that deposits those very finest particles already as soon as they enter the respiratory tract. And then the conducting airways, the green area in the lung here, has also a peak of deposition around 10 to 15 nanometer particles, and it's about 35% of those will be depositing there. But the highest deposition for the alveolar region are actually particles of 20 nanometer size. And as you can see here, it's about 50% of those particles that will be deposited in the alveolar region of the lung. So all different regions, depending on the size, will be targeted by particles. And so that's what we have to consider, and that's why it is so important to get some information, not only in the airborne state about the number distribution, which we talked just before about, but also about the size distribution. Yeah, what is so not just the number concentration, but also the size distribution. How many particles do you have of a specific size in the airborne state? So it gives you some idea where will they depositing, and what might be a potential target site for any effects.
And how are they different in composition from what we consider PM?
Well, PM is a general term, particular matter that includes the whole thing, from coarse particles to ultrafine particles. And each of them, again, it depends. I showed you that first slide with the different mechanisms of how they're generated. So for the ultrafine particles, as I pointed out, depending on the source, they can be very different. If you have a smelter nearby, then you expect to see a lot of metallic type particles, ultrafine particles in the air. If you have any other, let's say, diesel emissions from a diesel truck, if you're riding behind a diesel truck, the composition will be very different of the material that comes out there, and so forth. And for the bigger particles, the very big particles, it's mostly mechanically generated, so dust that has been coming off through the wind motion or other motions in the atmosphere. And the accumulation mode, the next smaller mode, again is particles. Many of the ultrafine particles have accumulated into this, but that's a mix of those different types of sources.
Okay, and my final question, how are ultrafine particles different from engineer's nanoparticles?
Yeah, I can probably go back to a first slide.
Unless they might be, or they...
There we go. Cool. So this shows scale, nanoscale materials on a scale from, again, between 1 and 10 and 100 nanometers here. And there are many diverse different particle types, and I listed, I can show a few here, but it shows also the size for things that we know about. So baseball here at the very right-hand side is, of course, huge. But here, with respect to the nanoparticle size, they belong proteins, even molecules, the fructose molecule shown here, and viruses. So they're all in that same size range as the ultrafine as the nanoscale materials here. And as I said before, these are made on purpose to have a specific property and functionality which makes them desirable. So you may have heard about buckyballs. They look like little soccer balls. It's all elemental carbon. And then again, elemental carbon in terms of carbon nanotubes. They are long, elongated structures consisting of either one layer of carbon or several layers, 2 layers, or so-called multi-walled carbon nanotubes. And then we have simple plates of elemental carbon, graphene. They are very thin, 0.34 nanometers as shown here, and can be of variable length and width. So these are all these different types of materials, and there are many, many others, of course, that are continuously generated. Also, there are nanopart materials, not just of a pure structure, for example, let's say TiO2, titanium dioxide nanoparticles, but there are efforts also to improve their function for specific purposes, let's say for solar cells, and to put some other materials on top of them, like vanadium or any other metals, so they will be doped, that's the term, and that makes them again toxicologically and also physically different.
But never considered pollution? or what?
Depends on how you define
qualities?
pollution. I mean, because they are intentionally made, we, as opposed to, and I don't know how you define pollution. If you define pollution as something that is due to unintentional contamination of the environment, then it would not be pollution. But we know that we need to be very careful. To give an example, I mentioned the carbon nanotubes. They have this fiber-like structure, and there are some studies showing indeed that this fiber-like structure makes them, I should be careful here, but makes them look similar like asbestos also in terms of the effect. There are some studies out there. But here again, that's a very important question in nanotoxicology and ultrafine particle toxicology in general. The issue of how much do you use in a study, the dose issue. And you can take anything you like, even water, give high enough of dose and it will be toxic. And that's a big issue that we need to always carefully consider and remember of.
So this is an important area
Oh,
of
yeah,
research and study.
Yes.
Thank you, Dr. Oberduster, for a fine introduction
Well, you're welcome.
to ultrafine particles.
I'm sure you get some more details from the co-speakers.
I'm sure I will.
Yeah. All right.
And you
Thank
can go
you.
back to listening to somebody else's
Yeah,
presentation.
Take that out here first.